Okay. Good afternoon. Thank you to the organizers for giving me this opportunity to speak. So my name is Kim, and I'm a PhD student with Anne Davis at the University of Cambridge. Everything okay? Can I be heard? Can I be heard? Good. And I'm going to tell you about hydrogen and how it relates to modified gravity today. So most of what I'm saying is based on this short paper that we published a little while back. So this talk and the one that sort of follows immediately after it is going to be a stark departure from the main theme of this conference, which has been the cosmology and astrophysics of modified gravity, as you know. We're going to spend some time thinking about laboratory tests and small-scale tests of these theories. I think I'm preaching to the choir here, and I don't really have to justify why these are important. But the sort of one sentence answer is, of course, that they provide complementary probes to these theories. They help you distinguish them, rule them out. So the greatest example, of course, is the prototypical chameleon model with the Rashad-Peebles potential with n equals to 1, blah, blah, blah. That has almost certainly been ruled out by these laboratory tests. So can we do better and so on. Anyway, when I say modified gravity, of course, I really only mean the chameleon-like theories. And I have to walk here to press this now. And the main reason I'm focusing on these theories, of course, is because laboratory tests are mostly sensitive to this kind of screening. It's a lot harder to try and invade Weinstein on the Earth, for example. So I'm sure everybody, if not everybody here, knows what a chameleon is. I'm not going to insult your intelligence by explaining what it is. I just want to point out a few things, specifically on the notation, just so that we're all on the same page. So the coupling, the conformal coupling between the Einstein and Jordan frame, I'm calling that omega. The chameleon here, I'm making it dimensionless, just so I don't have to carry blank masses everywhere, and I've just normalized with blank mass. I'm also assuming this axion-like coupling to the photon, which was mentioned earlier. Of course, the reason I can do this is it's not forbidden by symmetry, so let's just keep it around and try and constrain it with experiment. And then you can define these standard coupling parameters, beta m and beta gamma, as the couplings to, as the notation suggests, the matter and the photon respectively. Okay, I shouldn't stand so far from this. Right, what I'm going to say today is quite an old story. It's about hydrogen, how the presence of a chameleon really affects its spectral lines. And I say it's old because, of course, in 2011, this was known by Philip Brax and Claire Burridge. What they did, among other things, was to calculate how the chameleon affected the gross and the fine structure lines. And then knowing that this, whatever this small correction is, has to be within the uncertainty between the QAD prediction and the experimental measure. And of course, you can put a very weak constraint on beta m, and it turns out the combination beta m and beta gamma as well. Now, this talk is not going to update these constraints. The constraints have not improved. They are very difficult to constrain with this particular experiment. But what I am going to try and update is sort of our theoretical understanding on sort of how this very simple system behaves, with the hope of sort of giving some broader lessons, not to cosmology or anything like that, but specifically to the people who work in this sort of line. Maybe these calculations will help, will give you broader lessons of what to do in the future as well. Okay, so there are a couple of things that you can do sort of in addition to the paper in 2011. One thing that we weren't initially looking for, but we discovered it when we were doing the calculation again, was that if you really think carefully about all of the terms that you should keep when you do this linear perturbation, there are extra fine structure terms that enter into Hamiltonian. And so I think this is quite an interesting point. It's not entirely obvious where these terms come from if you don't spend too much time looking at them like I did. Okay, so I'll talk about that. I'll spend most of my time talking about this. Then you can play some fun games and say, well, if the atom weren't in the lab and if I just put it somewhere else, for example, around the black hole or a neutron star, or the space doesn't even have to be so strongly curved like that. If I'm in an unscreened environment, for example, if we believe that galaxies have these fifth forces roaming around, and if my atom is somewhere far away, outside where there's this sharp transition, if there is a big chameleon gradient, can I see an additional effect? Is it important? Is it observationally relevant? Can I use it to constrain things? Now, there's one more thing that we also did in the paper, which is to look at hyperfine structure. So as you know, this is when you include the magnetic dipole moment of the proton, and you get additional interactions, and you can calculate all the chameleon effects, blah, blah, blah. It turns out that this is not so interesting. Well, you can do it, and we do it in the paper, but the calculation is not particularly enlightening, nor do the constraints become better because of it. So just in case I bore you, I'm just going to skip this for the purposes of this talk. Finally, since this is a calculation that we are doing again, we decided, well, since the original paper did everything in the Einstein frame, as you normally would, let's do it in the Jordan frame this time. So I don't know if there are others, but this is now definitely one concrete example where we've done the same thing in both frames. Of course, naturally, you expect that you should see the right answer no matter what frame you use. And we do see that sort of up to a caveat. I think it's a reasonably big one, and I don't think it's been particularly appreciated. I'm not entirely certain of this, but I'll show it towards the end, and maybe we can just discuss it a bit further. Okay, I have to move here again. Right. Okay, so let me start with fine structure. So our model of the atom is completely the standard one. There's nothing funny going on. We've got completely empty space. We put down a proton. The proton is going to curve space-time. It's going to source a chameleon. It's going to source an electric field. Fine. These three fields we're treating classically, of course, and then we throw in an atom in the, an electron in the mix. The electron is going to interact with these three fields, and it's only the electron that we're going to quantize. Your typical standard story of how an atom is modeled. So because we're working in the Jordan frame, there is no direct coupling between the mass of the electron and the chameleon field. Instead, what happens, at least classically, is that the chameleon is going to back react on the geometry, even at linear order, and then it's going to come in via the Wehrbein and the spin connection here. So this is not the end of the story, and this is really where the source of these extra fine structure terms come from. If you have this coupling to the photon, you also have a correction that you have to pick up in A mu. And sort of the physical hand-wavy way to explain this is to say, well, this function here is making the vacuum behave like a dielectric, and so when you put down an electric field, it's going to cause the medium to polarize, and that polarization behaves like a bound charge, and the bound charge causes extra fields, blah, blah, blah. And so you should see a correction here sort of at order g, g being Newton's gravitational constant. Now, because this calculation is actually really easy to do, it's essentially one line, I think it's nice to just show it to you, just in case you don't believe me. So I'm ignoring the magnetic field, like I said, and I'm working in the static limit. So in flat space, the relevant Maxwell equations are these ones from spherical symmetry. Okay, so you can define the standard displacement vector field just like in electromagnetism in media. You define it as just the coupling, the product epsilon and E. Now, because we're working in spherical symmetry, you can easily show that the curl of D also vanishes. So because you've got divergence and curl of this vector going to 0, and you've got boundary conditions that there's a charge at the origin, this is standard electromagnetism now. The force is, of course, just the Coulomb field. But the electron doesn't couple to D, the electron couples to E, and so to get E back, all you have to do is you divide by this function again. Now, if you knew how to solve for phi exactly, that'd be great, but we don't. So we can still do it perturbatively. So you get, your standard bag Coulomb field, and to linear order in the correction, you've got Coulomb field times delta phi, this linear perturbation in the chameleon. So what does delta phi look like? This is, again, pretty standard stuff. You've got a VEV somewhere, phi naught, whatever the value is, and we perturb it linearly, and we can do this because the nucleus is light enough that it's not going to self-screen. The potential nonlinearities are not important here. We're also making one more assumption, and that is that the effective mass of the chameleon sort of around the atom is going to be small enough that the quantum wavelength is bigger than the atom. This is sort of really the ideal assumption. As Philippe likes to tell me, sort of here in Saclay in the 1940s, there were these people doing calculations about nuclear reactors, and they solved this nuclear reactor equation in the infinite reactor limit. What we're doing here is, of course, this experiment is happening in a vacuum chamber, and this approximation is the infinite vacuum chamber limit. And so these are really constraints that you put down that are agnostic about what the experiment will be doing. If you went down and you sat down and analyzed it properly, if this thing gets bigger, of course, these get Yukawa suppressed, and then their effects are smaller and your constraints are weaker. So this is the best you can definitely do. I should also mention, of course, I've been saying the word chameleon a lot, but I really mean any theory of that class. So this will work for the symmetron as well. As long as your VEV is not 0, you will have some beta here. In the symmetron, you will have a quadratic term, but that's typically smaller. But anyway, the translation between this and the symmetron is, again, dependent on your vacuum chamber and what it does. So this is really the simplest thing you can do. Okay, what does the Hamiltonian look like? It's pretty simple. You get one term here that came from the Wehrbein, so even though it went indirectly, now it comes back and you get exactly the same interaction. You've got a mass times the chameleon. This is this vacuum polarization causing a shift in electric field, blah, 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 effect that I've been talking about. And there's one more term that you get from the spin connection here. Now, it turns out that in spherical symmetry, the expectation value of this thing goes exactly to 0. So I'm going to drop it for now, but I'll come back and talk about it a little bit later at the end. I should point out, just in case you weren't wondering, this gamma naught is just a 4x4 Dirac matrix. And so I'm doing this completely for a relativistic electron. You don't have to. You can take the non-relativistic limit. Nothing really changes. But I've just left it there because it's not so hard to do it. And now the calculation follows true for Z all the way up to 137 or whatever you like, if you were interested in thinking of such things. Okay, so ignoring this term, these two terms give me 4 terms in total. So these two terms were the same ones that Philippe and Claire found, except for the gamma naughts. And these two new terms come exactly from this delta A naught. So what do they imply? So let's compare the second and the third term here. So we look at the third term, and you can see that it's going to be a factor of twice the proton to electron mass ratio, so about 4,000 times bigger than this term. And so you see that for a transition like the Lamb shift, so a 2p to 2s transition, this one has zero contribution because 1 of r depends essentially only on the principal quantum number. So of the remaining 3 terms that survive, this is the biggest term around, and so this dominates that transition. So you see, of course, that this extra vacuum polarization effect is not something small that you can't just throw it away. For certain spectral lines, it's definitely the biggest effect here. So if you don't include it, you predict the chameleon contribution to the Lamb shift that's about 4,000 times too small. Obviously, of course, in the grand scheme of things, this doesn't really matter. All these terms are incredibly tiny. You don't expect to observe them. But at least from a theoretical standpoint, it's good to know these terms are really actually there. Okay, we can do one more thing with these terms. So you see this one here. This goes like beta gamma squared. So if you think about the physical origin of this, of course, this is going to be the Coulomb field sourcing a chameleon profile, and then that chameleon profile sort of polarizing the vacuum, shifting the electric field, or if you like, in sort of particle physics language, sort of loosely, it's a chameleon-mediated photon-photon interaction. In any case, because it goes like a beta gamma, you can now constrain beta gamma independently, whereas originally you could only do beta m, and I said the combination beta m, beta gamma. So then you can plot one of these exclusion plots. You can see, so everything in the red and the gray, which is probably not so obvious here, is ruled out entirely by just the hydrogen experiment. You can say, you find that beta m cannot be bigger than about 10 to the 13.4, and beta gamma cannot be about 10 to the 19. So if you ignore these vacuum polarization terms that I've been talking about so much, then the exclusion region is just the region above this black line. So this is what Philippe and Claire found 6 years ago. So you see that there's this huge region of parameter space that's not inside the diagram that we've ruled out. But again, like I said, we're not really doing very well with these constraints. This region is completely ruled out anyway by other experiments. But at least theoretically, we have a better understanding of what this particular system is doing for us. Okay, that's all I really have to say about laboratory experiments. So let's play this game now, and let's put the atom somewhere else. Can we see something else? In curved spacetime, of course, the electron is going to remain bound to the nucleus, so it's not going to probe spacetimes very far away. So the standard thing you do, of course, if you pick Fermi coordinates and you write down the metric as a flat space plus some small correction. So if I keep it to linear order, then the only thing I pick up is this acceleration vector, assuming I'm not on a geodesic of the Jordan frame. I could, in principle, keep the quadratic terms as well. So these are going to be linear in the Riemann tensor evaluated at the point of the nucleus. Definitely for GR, it was done by Park and Pimentel in the 80s. But if you take these terms and you propagate down to the Hamiltonian, you get about 16 terms. They're all a horrible mess. They're such a pain. And they're all very small, so I'm just going to ignore them. I'm just going to keep them to linear term here for fun. I do the same thing for the chameleon. I keep it up to linear terms. And so what I have is just the contribution from the VEV. And now I've got a chameleon gradient sort of locally evaluated at the point of this nucleus. And because gravity also, in quote unquote, behaves like a dielectric, it's going to cause these corrections again. Anyway.
I mean, this is not a curved background, it's accelerated, right?
Yeah, exactly. So at first order, I'm well within my rights to ignore any cross terms between this new background effect I'm keeping around and these 1/r potentials I've calculated earlier. So at this order, all I really do is I have an additional contribution to the Hamiltonian. So everything here follows as before, and now I just have to figure out what this delta H is going to say. Good. I'm traveling. I'm moving faster than my practice talks. That's good. I've got enough time to say everything I want to say. All right. So you calculate delta H, and you get a term from the acceleration. You get a term from the chameleon gradient. And actually, because the acceleration is a metric effect, you've got lots of these indices. You get another of these 5 terms. But if you sub in some order of magnitude estimates, you find that all of these are about 10 to the 4 times smaller than this leading one. So for simplicity, I'm just going to drop all of these. These are not interesting to me. So if you stare at this long enough, and it doesn't really have to take that long, you realize that these terms are odd parity, and so they're going to behave exactly like the Stark effect. So sort of the short answer is that even if your atom didn't have an electric field, if there was an acceleration or a chameleon gradient, it sort of looks like there's an electric field around. Well, how big is this effect? Now it turns out that for sort of physically reasonable values, there is, I forgot to say this. So because it behaves like a Stark effect, to figure out what this does, you do the standard story again. It's completely degenerate perturbation theory. You've got matrix elements between the same degenerate states, between different degenerate states of opposite parity, and you do standard story, you mix it around, it mixes your eigenstates, you calculate the shifts, blah, blah, blah. But that story only works, of course, if you've actually got degenerate states. By sitting in this tower here at H0, which is sort of scale 13.6 eV, and somewhere down here is delta H. In the middle here is definitely what I've been calling, what I would call QED corrections. So these are the actual vacuum polarization effects from loop corrections, relativistic recoil, finite size of the nucleus effects, blah, 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 all of the kind of things that you can see in the standard hydrogen theory literature. And these will generically break the degeneracies between your opposite parity states. And so by the time you reach sort of this energy scale and you want to act with this operator, you realize you don't have any degenerate states left. And so these terms are really completely washed out by these QED corrections. Now you can turn it around and say, well, how big must these terms be so that I can actually see it? So treating this term in isolation, you realize that you need A to be about 10 to the 15 Gs, here being the acceleration on Earth, so 9.81 meters per second squared. Or treating this term in isolation, you require that this combination, the chameleon gradient, must be about 10 to the 19 Gs, so highly unphysical numbers. Neutron stars, for example, have 10 to the 11 Gs at best for a reference. Okay, so obviously this is all disappointing, but this is what you expect. You don't expect sort of curvature things to affect what's happening in the atom on the atomic scale. It is sort of nice that we sort of done it definitively. This is the answer. So there's one more thing I want to talk about in the less than 5 minutes I have, which was this term here that I've dropped in the Hamiltonian that I constructed right at the beginning. Like I said, this goes away, the expectation value goes to 0 because we work in spherical symmetry. But spherical symmetry is not a generic thing. It's completely, you can very easily break it, for example, if you include the magnetic contribution to delta phi. So in general, this thing has a number and it's sitting in the Hamiltonian and it has an effect, small as it may be. But if you do the entire calculation again in the Einstein frame, you find that this term never appears. And so you've got two different theories for the frames that you pick. So what's going on? Can we understand this? Is this theory really frame dependent? So again, the story is quite simple, of course. If you work with the Jordan frame, this is naturally what you want to call the electron. You have the standard Dirac action here. So now I want to move to the Einstein frame. I do the standard stuff. And because there's a spin connection sitting inside here, it's going to spit out exactly this orange term that's responsible for this extra contribution in the Hamiltonian. But now you say, well, I don't really like this omega cube sitting in front of my kinetic term, so let me get rid of it by the spin connection. And now I'm mixing what I wanted to call the electron with the chameleon. And then, of course, that thing, this minus 3/2 is going to kill this plus 3/2 as you would expect. But so you see that if I were a person that was inclined to work within the Jordan frame, this is what I call the electron, and I do the standard story, and I quantize and construct the Hamiltonian, and I will get a spin contribution. And if I decided I wanted to call this the electron, then I would get the same thing, bar this contribution. So we see that at least certainly within this perturbative semi-classical approach, which is what you want to do when you quantize the electron, you don't want to quantize all of the four fields at the same time. You are definitely sensitive to these field redefinitions, and at least at linear order, you just differ by this one spin interaction. But that means this demands a choice from us, really. You can't say this one is the electron and this one is the electron. One of them is the electron, and one of them is going to be this mixed electron chameleon degree of freedom. And I stress this is because the electron, we typically treat it differently. It's sort of the only thing that's quantized, and it's sitting in something else that's completely classical. So at least within the confines of these kinds of calculations, it seems like you have to make a choice, but the choice is not entirely obvious. Obviously, this one seems more natural because it's non-minimally coupled, it's canonically normalized, and it's continuously connected to the definition of an electron in the standard model. But then this one is certainly a lot easier to work with. You don't have any of these derivative interactions in the action, and so on. So I don't want to go so far as to make a choice for anybody, but I just want to sort of make the point that there is this distinction, and it's probably important to be aware of it when doing these sorts of calculations.
Sorry, can we rescale the electrons?
Well,
The issue is that if you're in Jordan frame, then the metric will contain, physically the value of the metric is still the same. The metric will contain perturbation, which is the one that is sourced by the electron. So it's not this is the problem per se, it's the fact that you're neglecting the fact that the electron is sourcing the metric.
Yeah. No, you're absolutely right, and it's because we sort of do this electron on top of everything else. Had we done everything exactly, I don't think you would see a problem.
Yeah, the right way to do it in both frames.
Yeah, so there has to be a better dictionary between the two frames than sort of what's typical, than the naive thing that you would do, I think. So you're essentially saying we have to keep track of the electron, what it's doing to the metric, and typically we don't. Right?
You do.
Well, maybe we can discuss this a bit later.
Yeah, I mean, it's the same more complicated between, you get exactly the same answer.
Yeah. Well, I think so. So yeah, I think sort of, yeah, okay. I don't think I have anything much to add on that. Well, I'm essentially done now at this point. So let me just summarize. So hopefully I've convinced you that with these calculations, we now have a more complete picture of what hydrogen does in these sorts of theories. Of course, these constraints from this particular experiment are particularly uncompetitive, and that's sort of to be expected. You've essentially got a large hierarchy of scales. It's the Coulomb force that's setting the effect that you're measuring, and the gravitational force that's setting the effect you're trying to constrain. So perhaps the most important thing is this additional effect, these vacuum polarization terms that cause a correction to E, and that's something that has to be taken into account in the Hamiltonian as well. And well, this thing we can talk about more. It's certainly non-trivial, this transformation when working with either frame. Okay, thank you very much.
Thank you. Questions?
Well, for the first part, have you looked at Earth-Wash? Because you would expect that this coupling would induce different elements to fall differently in the presence of phi. So I could imagine that those measurements are extremely precise. So I could imagine that.
Oh yeah, definitely. I mean, people have definitely looked at Wash and understood the constraints from that. There was a great paper yesterday on the archive by Claire Birch and Jeremy Sackstein. They've just updated their latest review on all of these laboratory tests and some astrophysical ones as well. Yeah, I mean, this talk has really only focused on this one experiment. We definitely are aware that there are so many more that do a lot of a better job. And as I said in the beginning already, the prototypical chameleon has almost essentially been completely ruled out, bar a tiny sort of sliver inside the parameter space.
More comments?
Can you do? I mean, do people do experiments on this where you just send a charged particle, and I guess you would expect that there would be some sort of, in the presence of a gradient of the scalar, you expect some sort of deviation from the path on the same level as in gravity, which I presume is observable, no?
That sounds like something people have done, but I'm not an expert on all of the experiments, so I want to refrain from commenting too much. But it definitely sounds like something that's been done and something that's already been accounted for.
They actually do it with neutrons, and they compare to the energy levels of the neutrons in the gravitational field of the Earth, which is quantized. So it's actually quantum mechanical. You're not looking at the trajectory.
So I was thinking this is for a situation where you have a...
Okay, if it's charged, yes. Okay, charged, no. But it's easier with a neutral particle.
But then it doesn't come.
No, that's not the same, yeah. More comments? If not, thanks a lot.
Thank you.